All right, line A5, learning task number 3. We're going to talk about characteristics of a delta type of connection. Delta type of connections are going to be more rare for supply sides than Y connections. They used to be more prevalent. BC Hydro used to hook up more of them. At this point, they have changed a lot of the type of services that they're going to go and service, and because a lot of those reasons that we gave inside of the why for why we like to go and have the ground at neutral, because a lot of those make sense and increase safety, BC Hydro is less and less apt to put in a delta type of connection service. You can still find them privately. You know, if somebody has a high voltage connection coming in, one of the plants that one of my brothers works at as a instrumentation electrician, they come in at 25,000 volts, they're in at 3-phase, but then they drop that down into multiple smaller services, you know, 600, 347, 122, 8 to go and distribute to some of the other components on site. As they go and do that, sometimes what they're going to do is as they come off of that, you know, I'll just draw it over here, 25 kV slash 14.4 kV line that they're coming in at. They come in from there and then they distribute out and across through a pile of transformers. We'll just kind of draw them here as a one-line diagram to a bunch of the other areas inside of their plants. And as they do that, they have got some of these areas that are motor loads alone. And those motor loads work particularly well off of a delta service because a 3-phase motor, you're going to find out, doesn't need to go and have neutrals. So they're more common in this type of an application as part of a subservice, not as the actual BC Hydro service, unless you're dealing with an older installation. The delta service looks something like this. Over here, they're showing us a service that is coming in at 120 volts per phase, which means that this phase over here is 120 volts, this one's 120 volts, and this one over here is going to go and be 120 volts. And unlike the Y values, which had a different phase and a line voltage, here inside of my delta, my E phase is going to be equal to my E line. If you just take a look at that, you're going to see that, yeah, this makes sense. If that's 120 volts, we see it directly across from this line connection to this line connection over here. It's a wonderful thing. What we do have, though, that is going to be different off of our delta system is that our phase currents are going to be a little bit different. Over here, if I have got current that is traveling through here, I'm going to go and have it in phase with my phase value of voltage, but then it's going to go and hit this node over here. And according to Kirchhoff's law of current, the sum of all currents entering a node is equal to the sum of all currents that exit that node. And we're going to go and have just a different layout to the way that that is done. Let's take a look at how that is going to go and actually be done. Over here in your binder, you're going to go and see across your pages 30 and 31 that there's a whole pile of math that's going to be once again laid out inside there. Once again, they're using a lot of basic trig, SOHCAHTOA, and stuff like that. They're breaking down what we have as vector coordinates. You know, they can take a vector and they're breaking it down to X and Y positions, and then they're using those to add together to go and create the math. We have got that calculator, the Sharp EL520, and we're going to go and use that for the bulk of what we're looking at. Where do we get these values of currents from? Well, the current values are just going to be by examining a node. If I take a look at this node over here, I see that I'm going to go and have, because I've got a big A going over to a little a, I'm also going to go and have a big B going over to a little b over here. And if we took a look at the first the learning task inside of here, we saw that when we alternate going around the outside of our alternator, we had big A, and then we'd have little b, and then big C, and then little a. I'm drawing them poorly over here. Then big B, and then little c, that were going around the outside. And we saw that whatever I had for polarity going in over here, if my A was peaking, that I was going to go and have, a small amount of current going through C in the opposite direction. If you take a look at that on here, we can see that if I'm going to go and have my current that is traveling through in one of these directions, we're going to go and have corresponding smaller currents that are going to go through the other. And because all we're doing is making this connection on the outside, taking this one over here and connecting that one with my little b over here, we're going to go and have a couple of currents that are going to be adding together, but they're going to have different values of voltage, and that's just due to the way that we change the directions inside of these windings. Don't stress too much about it if you don't quite get what's going on with that. The big thing that we're going to have to look at is the fact that when one current is going in one direction, we're going to go and have other currents that are going to be going in opposite directions over here facing through. And do note as well that all the currents go and form a complete triangle going all the way around this. We'll get to that point in a second as well. First of all, how do we go and calculate our value of line current? Well, we know that our line current is not going to be the same as our phase current because we see the phase current is leaving, but then over here we've got another phase current that is entering, and so therefore we have to have some sort of a vector sum that's going to add up over here. We can go and do this by using our calculator. We're going to go back to that sharp that we had over here. Before we do that, let's just go and grab these values over here. The values that we're taking a look at are going to be these two. 10 amps at angle 0 and 10 amps at angle 240 over here. Both of these are going to be going into this node, and so we're going to be able to go and pull both of them out to go and figure out what we have for our line off of this one. Before we do any calculation with them, we just have to take a look at the node once again. If I take a look at this, I see that from this node, I'm emitting one of these, whereas the other current is coming back into that node, which means that there's going to be a difference. Basically, we can take this value over here, we're going to have that as a positive value, and we're going to subtract this one because this one's coming back out of that same node. Let's go and do that on our calculator over here. So I'm just going to go and take value of 10 angle 0 minus, because this thing is going the opposite way out of the node, 10 angle 240, which is going to go and give me a value of 17.3 as being my total amount of line current, and that's happening at an angle of 30 degrees. Compare that with the result that they have at the very bottom of the equation on page number 30. Page 30 is just showing the exact same layout that we're doing. They're just doing it through all the X's and Y's or the J operators. This one, we're just doing it quickly through the calculator itself. Either way, it's potato, and we end up at the same value of line current, which is going to be this one over here, 17.3 at an angle of 30. Do note that it is going to be at 30 degrees, which means it is going to be my line current on A line over here, the capital A is which line we're looking at, is going to be 30 degrees different than my phase current that I'm going to go and have over here as well. There's also going to be a relationship between this line value of voltage, 17.3, and this line value of, or this phase value of current over here. If I go and take 17.3 amps and divide it by 10 amps, I can go and find out what that relationship is, and that relationship is equal to 1.732, which should be a familiar number to you by now. We recognize this number as root 3 over here, 1.732. In other words, my I line, this over here, is going to be 1.732 times larger than my phase, because it is going to be made up of this phase current as well as this phase current, which is going to be aiding it as well. We can develop a set of formulas off of that. Once again, we can say that I line is equal to I phase times root 3. And if I want, I can go and take that formula and I can go and divide out the root 3 to go and isolate for I phase. That would be I phase is equal to I line divided by root 3. And this is going to be for any sort of a delta system. Delta systems are wonderful on their voltage for the fact that my phase and my line voltage, E line, is equal to E phase. Real simple to calculate like that, but it's the current that we have to take care with, because we're going to see that relationship, that root 3 that's going to be placed throughout all of these. Using that math that we did there before, where we took a look at which one is entering and which one is leaving, we could go through and figure out from there, the rest of our values of line currents. And the values of line current would work out to become this 1.73 at 150 and 117.3 at negative 90 or 270 degrees, whichever one you prefer to go and utilize. Altogether, all of those vectors could then be put together to form something like this. If we take a look at our very first 10 amps that we saw at angle 0, that was my current going across from A to C through the actual phase, going across here from A to C through the actual phase. Let me just move this out of the way here so we can see it. 10 amps going across from A over to C over there. That was what I had, and then we found out that my total line current on that line A was going to go and become that larger value, 17.3 at angle 30 degrees. And we see that there's that 30-degree displacement between my phase values and my line values that I'm going to go and have across here. Refer back to your Y. On the Y, there was a 30-degree difference. The 30-degree difference on the Y was to do with the line voltage and the phase voltage. On my delta, the 30-degree is between my line current and my phase current. Last thing that I want to note is that if I were to take all of these currents over here, my line currents, and add them all up on a balanced system, I'm going to go and end up at a net zero. If I take this IA, it's coming out like that, and then I add it to IB, coming down like that, that's that line there, and then I take my IC, add that one, tip to tail, I would see that I would end up back at the exact same value that I had here before, which would be 0. And you can punch that into your calculator if you want, 17.3 at angle 30 plus 17.3 at angle 150 and 17.3 at angle 270, and you're going to come out to a value of 0 at 0 degrees. On a balanced three-phase system, all the current that is being delivered out is going to be coming back in and give us with a net value of 0 off of here. Ungrounded systems on delta are a bit of a problem because when we create a delta system, there is no point to go and ground down that system. In essence, it's as if the ground itself goes and exists at an imaginary point on the inside of that. And all these other lines are just kind of floating around that center point over there. Normally, if we don't have any sort of an issue on our lines, we're going to be completely fine. I'm going to just draw out my lines over here. We're going to go with an A phase. We're going to go with a B phase. We're going to carry these ones out. These are going out to loads somewhere else. It's my distribution system and my C phase, like that. The picture's a bit disingenuous in that it doesn't show those lines going all the way out, but those are my lines going out. If I end up with a ground fault on just one of these lines, so right now I just want you to go and ignore these lines all over here, okay? So all of that assembly over there, we're just going to ignore it for the time being. But if I ended up with a ground fault right over here, it is not going to do anything to the system because there's no place for that current to go and flow back to. And there's no other connection to this floating ground that we have inside of the system over here. So a single ground fault on a delta system cannot be tracked. It can cause problems, and as soon as there's a second one, we would go and end up with a dead short. If we'd end up with a second line fault over here, then all of a sudden we would have this path over here, which would be a very, very bad path. It would be a dead short path from one to the other. We want to avoid that, so anytime that we do get a single ground fault on our system, we want to be able to go and identify that. And the way that we do that is through these lights over here. If you take a look at these lights are all connected together in actually a Y type of formation. So if I were to go and look at these lights, I could actually redraw these lights in the very center of here. If these were little tiny lights over here, I could redraw them right here in the center as if that were grounded down. And if you take a look at that Y connection, you know that there's a voltage differential between my line, voltage E line, what's going across from here over to here. There's a difference across there compared to my phase voltage, what I'm going to go and have going from the center part over to one of my phases. So normally, and I'm just going to ignore the rest of these here right now again. Normally what happens is these lights over here are only seeing less than full line-to-line value. It's actually going to be a value that is going to be 57.7%. And this 57.7% is actually, it's another interesting number over here. It is 1 over root 3. Take root 3 and invert it, you're just going to end up at that 57.7. Normally, they're going to be glowing fairly dimly. However, as soon as we end up with a fault on the system, like what they have out here, where one of these lines gets grounded down, basically, because this is ground and because this is ground over here, that means that this current is going to get completely bypassed, going across from here to here. We're not going to go and see anything over there. That light, there's no potential voltage across it because this point is the exact same point as this point, which is the exact same point as this point. Point is the same, it's tied to ground. Point is the same, it's tied to ground. No potential difference across that lamp. That lamp is going to go dark at that point. All right, let me erase a whole pile of lines over here, and let's just trace those current lines through one more time on the larger drawing over here. Let's put those ones back there, my B phase and my C phase. If we end up with this ground that goes and happens over here, that ground is going to go and take out whatever light is attached to A. If I take a look at A right now, turn all these lights on right now. If I take a look at A right now, on either side of it, I see that this side over here is attached to ground, and I see that this side over here is attached to ground. No potential value of voltage. Therefore, this A light is going to go dark. The other two lights are actually going to go and become brighter. They get a little bit brighter over here. And the reason that they're getting brighter is because now all of a sudden they are going across from full line-to-line values. Take a look at this. Right now, if this is where my ground fault is over here, that means that's the same point. I can just follow along with my finger as if I had my ground fault tied right over here. And if this is ground right over here, then this is ground right over here. It's the exact same thing as if I had a line connecting up and across to that point, which means that if I look at this light, the C light over here, I see that the C light is, I'm just tracking along here, attached right over here, and it is attached all the way across, so I go through the light across to ground, which is at this point over here. So in essence, it's as if the C light now got stretched across from line to line over here. The C light is going to end up going brighter. Same with my B light, because the B light is going to be doing the same thing. It's as if it were attached going across from line to line over here as well. Both of these are going to go brighter. The other one is going to go dimmer. It's going to go have shut off. And that's how you tell when you've got a single ground fault on that system. At that point, you're just going to go through, trace it. There's a bunch of tracking methods for sorting out those ground faults. We'll take a look at that inside of the grounding module. And then you're going to be able to find that thing and remove that ground fault before a second one occurs. We also have another specialty system we're going to take a look at. This is going to be called my 3-phase 4-wire delta system, and it is a oddity. Chances are most of you will never run into it in the field. These are not put in as brand new services. These are usually going to be put in, dropped off someplace where I have got a delta system, and I've got primarily motor loads, because delta is really good for motors. So it's going to be, let's just go and say it's like 90% motors, and maybe like 10% offices and lighting and something like that. A good place for this would be things like, gravel pits or stuff like that, where most of it is going to be motor load driven and you only need a small amount of single phase power. What we can do on a 3-phase delta connected system is we can go and center tap. What I do want to point out over here is that this drawing is a little bit confusing in the way that they're laying it out. This side over here is my supply, my transformers. You see that from the fact that we've got those bumpy looking windings. This side over here, the blue side, is going to go and be my loads that I'm going to go and have attached to my system. Let's start by looking just at the transformer side over here. For us to go and create a 3-phase delta system that's going to be a 4-wire, we're going to go and create the standard delta type of system. But then what we're going to do is we're going to take one of our windings, and it's always going to be the B to C winding. We're going to take that B to C winding, and we are going to go and ground it in the very center. And when we ground it in the very center, we're going to create a neutral. That means that if this thing was 240 volts across from C to B, half of that 240 volts would then become 120 volts, 120 volts, and from this point to this point becomes 240 volts. We've got a 240 volt delta system. Each of the other ones is also going to be 240, 240, 240. But we've taken the one now and we've split it in half, so we've got this single phase as well. Following that along, you can see that the white conductor, this one over here, comes across, it acts as my neutral, and that I'm going to go and have my B and my C, my blue and my black lines, that are going to be connected to my single phase load. Right now, I want to ignore part of my loads. I want to ignore this, and I want to ignore this, and I want to ignore this right now. And I only want to go and take a look at that single phase load that we have across there. So we'll just draw out our connections for that. From here, I see that I've got from my transformer, I've got my blue line going through to here. I see that I've got my black line going through to here. And I see that I've got my neutral, my white line or my gray line going through to here in the center. And then I've got loads that are connected across here and across over here. Any current that I develop is going to go and have instantaneously, there's going to be a positive here, which would mean the other side of the winding would be negative. And remember, it's AC, so it's flipping around all the time. If I'm in reference to this positive, this point over here is a slight bit more negative. And if I ignore those two, in reference to this negative, this point is also a slight bit more positive. So half to half, it kind of looks like we've got a positive negative point right in the center there. That's because this point is more positive in relationship to point B, but more negative in relationship to point C. What that means is that at any given instant, we're going to have a blue over here that's going to be a positive. We see that we have the black over here that's going to be a negative, and that we are going to therefore have current that is going to go and travel through. I'm going to be able to deliver current from my negative. Let me just change the color marker over here. We're going to go to green. I'm going to deliver current along through here. That current is going to go and travel through my load from negative to positive. And if it's only that side that's operating, I can then take that current all the way back through to here, and it can circulate through that winding and come back out. Same as on my other one over here, I'm going to be able to deliver current down here that is going to go negative to positive through and follow that line over there. So in essence, we have got a single phase system that is developed off of this winding over here. At the same time as we have that single phase system, and I'm just going to erase all of that, we also still have a three-phase system, and that three-phase system is going to be these three windings over here. They could be a three-phase motor or anything like that. We are going to be able to go and deliver along all of our lines, deliver current. The current is going to split, come out here, and then come back along there, come back along there. We've got action on all three of our lines on the B, C, A phases all at the same time. So it's handy if you don't want to have a ton of different components on site. However, it's a pain as well because you just rely off of one single center tap transformer. Now you got a bunch of special rules as well. The code is going to refer to the one leg as being the high leg. The A leg over here is going to be the high. The grounded conductor, this conductor over here, this neutral, they call it a grounded conductor, has to be in a compartment provided for single phase. So you're going to have to go and have a single phase panel that's basically going to go and incorporate all of those sections over there. And the A phase has to be in a completely different section of the panel. You cannot buy a three-phase panel, put that three-phase panel in, and then, connect A, B, C and the neutral into that one, because what actually happens is if I were to go back to this one over here, calculate our voltages, if I were to go to the value of 240 volts that we have for each of these, I would see that half of that would be 120, half of that would be 120. But I know that from here to here is 240, and I know that across from A to B is also going to be 240 volts, which means that if I were to look at this, I could actually draw a right angle triangle over here, and I could go and use just my basic Pythagoras to go and figure out what this value is going to be right over here. Be real simple. You're just going to go and do 240 squared minus 120, this section over here, 120 squared, and then you're going to go and take the square root of that entire thing, and you're going to go and end up with a value coming across there of 208 volts. Which sounds fun, sounds like a three-phase voltage, but this is not the correct place for us to be using that 208 volts, because this 208 volts would be measured across from this point over here, which is a grounded neutral over to a line. So it would be a phase value of 208 volts. Very dangerous, because if you as an electrician walk into some place, you got a 120 volts piece of equipment and you hook it up onto a three-phase panel, and one of those legs is actually 208 volts above the ground, A, there's a lot of danger to you accidentally just touching it, and B, that equipment is just going to blow up as soon as you go and turn that thing on, and you have potential for arc flash fire and everything else that's going to be associated with it. Once again, all of these vectors can be laid out over here as a vector diagram. Does this vector diagram do a lot? Yeah, not really a lot. It's the 4-wire AC source over here. You could use it to go and explain a few components off here, but more than anything, it is going to go and give you, cause confusion. So I'm not going to bother going over top of it. Once again, if vectors are your jam, by all means, associate yourself with it. But since most students get lost off of it, and since we don't really need these vectors to go and explain it, we're just going to go and bypass this drawing here right now. All right, that's that.